Yesterday we developed the idea of the heliocentric theory of the solar system, the idea that the Earth revolves around the sun. We looked at the steps in the development of that model of the solar system. And then we went a little bit past that, in fact. We not only identified that the Earth does revolve around the sun and sort of the other planets, but we looked at how they revolved around the sun. Okay, what's the path of them? What's the shape of the path? What are some of the intricacies of that path? Let's take a look at the development of that model here first, and then we'll talk about the model itself. First guy we talked about was a couple thousand years ago. In fact, about 2,500 years ago. We talked about Aristotle, and then we also talked about Ptolemy, who was about 500 years later. Both said essentially the same thing. The Earth is the center of the universe, which seems so foreign to us now. We know that the Earth isn't the center of the universe, but we know that, as we said yesterday, because people have told us. People smarter than us have told us that the Earth is not the center of the universe. The sun is the center of the solar system. If we look up in the sky, though, in the morning, the sun rises in the east. It circles around and sets in the west. That would tell me, if I didn't know any better, that the sun is revolving around the Earth. So it's not so far-fetched. It seems like it now, but if we take a step back from it, it's not so far-fetched. But we still know that it's wrong. Zoom forward a couple thousand years ago, or a couple thousand years, to Copernicus, 16th century, mid-16th century, the heliocentric. Helio means what? Helio again? Sun. The sun-centered theory. All the planets, including the Earth, revolve around the sun. Think about that for a second. Okay. Intuitively, we look up in the sky and we say, oh, the sun revolves around the Earth, right? Okay, my 3-year-old son doesn't know anything about the heliocentric theory of the solar system or the geocentric theory or anything else. He looks up and he sees the sun over there at one point in the day. He sees the sun over there at another point in the day. What's he going to think? What's my 3-year-old going to think? He's going to think the sun's moving, right? But you guys have all experienced this before. Okay, you're in a car. You're sitting in a parking lot. Okay, you're nodding off a little bit. Okay, just sitting in the parking lot as you're waiting for your mother to come out of the grocery store or whatever the case may be. The car beside you starts backing up. And you kind of wake up in a little bit of a daze and you think you're going forwards. Right? You ever notice that? You think your car's moving? It doesn't matter whether the car beside you is moving or whether you're moving. It appears to you the same way. If you're looking at that car beside you and it's backing up, you can't really tell the difference, at least immediately, whether it's backing up or you're going forward. That make sense? It looks to be the same thing. So the sun is revolving around the Earth. That's what it looks like. Well, why can't it be the exact opposite of that? The Earth is revolving around the sun. It would look the same, right? Intuitively, we think the sun is revolving around the Earth, but the Earth revolving around the sun would give us the same effect. So the Earth is revolving around the sun, hence the heliocentric theory. All the planets, including the Earth, are revolving around the sun. Next, I'm going to cover this one up. Here's the guy that took naked eye observations of the stars, of the planets. Okay, took some times, took some angles, took some distances, and so on and so on and so on. Then his assistant did some stuff with that data. What's his name? He's also, by the way, the P guy. What's his name? Tycho Brahe. You got to remember this guy, right? He's the guy that died of a bladder infection, held his pee too long. So Tycho Brahe, in the late 1500s, along with his assistant Johann Kepler, this guy is a lot better known, right? Because he did a lot of stuff with the data, not just collected the data. Collected some naked eye observations, including times and distances and angles and so on and so on and so on, that his assistant Johann Kepler used to create 3 laws. 3 laws that we're going to address in just a second here, that described the motion of the planets. Not just the fact that the Earth revolves around the sun, but how the Earth revolves around the sun. Like, what is it? What does the path of the Earth around the sun look like exactly? What are some of the properties of that revolution of the Earth around the sun? Well, it starts with the law of elliptical orbits. And this is the one that everybody looked at yesterday and think, what? There's 2 suns? There's one sun. The sun is either here or the sun is here. The sun is where it is. And then the Earth revolves around the sun such that the sun will be at one of the focal points. So let's say the sun is here. Well, the Earth could have revolved around like it is in the diagram here, or the Earth could have revolved it around it like this. Okay, the sun would be at the first focal point for this one, and this for this ellipse, and it would be at the second focal point for this ellipse. Doesn't really matter. The Earth could have revolved around in either spot. The bottom line is the Earth revolves around the sun, and it revolves in an ellipse with the sun at one of the focal points of that ellipse. The second one, they kind of get a little bit more confusing as we go. The second one, the law of equal area, said that, look, if I draw a line that joins the sun to the Earth, in a certain amount of time, that line that joins the sun to the Earth, now the Earth is in a different spot, right? That line that joins the sun to the Earth will sweep out a certain area. That area in green, whatever that is in meters squared. Fast forward 6 months, a line joining the sun to the Earth will sweep out another area in a certain amount of time. That other area is indicated by the green as well. If those two times are the same, in other words, if T1 equals T2, if the time that we looked at from here to here is the same as the time from here to here, then area 1 will equal area 2. These two areas may not look the same. Okay, one's short and fat, the other is long and skinny. Okay, but in the end, the areas are the same if those times are the same. So what? What's the big implication of that? What do we say about the motion of the Earth around the sun and its speed? What did we say yesterday? As the Earth gets closer to the sun, the Earth is going around here, it gets closer to the sun, what happens to it? Yep, it goes faster, speeds up. As it gets further away from the sun, it starts slowing down. And it speeds up. Slows down, not quite that dramatically, but okay. It's a little bit more gradual than that, but I'm not quite coordinated enough to draw it gradually like that. You guys get the picture, okay? The other thing I want you to remember is that the ellipse isn't nearly as pronounced as this. It's much, much closer to a circle than I have drawn here, which means the difference in speed wouldn't be nearly as dramatic as it would show on this diagram as well. Okay, we have it exaggerated so that you can see that there is an ellipse and that there is a difference in speed. It's just not nearly as great as we have here. The third one, the final one, the law of periods. Let's say we got the sun. We got a bunch of planets revolving around the sun. It used to be 9, then they said there was 10, and then they said, no, this one doesn't count, this is not a planet, it's a little minor thing. Okay, where are we at now? I don't even know what we're at now for planets. Okay, it changes all the time, it seems. Okay, let's identify a couple of them, though. Let's look at the Earth. And let's look at, which other planet do you want to look at? Saturn, okay, Saturn. The Earth revolves around the sun, as does Saturn. There is a certain period of revolution of the Earth around the sun. Does anybody know what that period of revolution is for the Earth around the sun? How long does it take the Earth to go around the sun? Yep. 365 days. It's actually 365 and a quarter days. That's why every 4 years you have a leap year. Okay? And it's not even actually quite 365 and a quarter, because every I forget how often it is, every so many 100 years, they actually don't do the leap year on the 4th year. Okay? There's a rule for it. And I can't remember what the rule is, but bottom line is it's not exactly 355 and a quarter, but it's real close. Okay, so that most times that leap year works out. The time that it takes the Earth to go around the sun is about 365 and a quarter days. The radius of revolution, how long does it take, what's the radius of the Earth's path around the sun? Well, it varies a little bit. Okay, but there's an average value. I can't remember what that is off the top of my head, but it's on your data sheet. Maybe 1.5 times 10 to the 11. All right, not even close. And It varies a little bit, but the average value would be that 3.85 times 10 to the 8 value. Oh, that's the moon. Oh, maybe I was right. Oh, 1.5 times 10 to the 11. I'm vindicated here. Saturn goes around the sun as well. I don't know what the period of Saturn is around the sun. I don't know how long it takes for Saturn to go around the sun, but it's not the same as the Earth. There's a certain radius, or at least an average radius, of Saturn's path around the Earth as well, or around the sun as well. There is a certain value of Kepler's constant that is equal to TE over RE squared cubed, right? T squared over R cubed, which is the same value as T squared over R cubed for Saturn. Okay? That value is Kepler's constant for the sun. Now, if we looked at some other mysterious star somewhere out there in the universe, let's call it star X, with two other planets revolving around star X, we'll call them P and Q. There would be a T and an R for both of those. There would be a Kepler's constant for planet or for star X. That Kepler's constant would be equal to T squared over R cubed. These two Kepler's constants would be the same. Even though we're using data for planet P, for planet Q, Kepler's constant would be the same because the thing that was being revolved around was planet X, or was star X. These two Kepler's constants would be the same. Even though we're using data for planet Earth and planet Saturn, the thing that's being revolved around, that is the sun, is the same. These Kepler's constants would not be the same. So Kepler's constant is a property of whatever's being revolved around. We use data for whatever's doing the revolving, but Kepler's constant is a property of what's being revolved around. Does that make sense? Now, that allows us to set these two equations equal to each other and solve for a property of Saturn by using properties of the Earth, or to solve for a property of planet P using properties of planet Q. Okay? Good news is we don't have to do any mathematics with this. We kind of have to have a general understanding of a relationship between T and R and how it can be used to determine the property of the star that it's revolving around, but we don't have to actually crunch any numbers with it. All right, that's what we did yesterday. Does it make sense? What we haven't talked about yet is why. Here's how the Earth revolves around the sun. There's lots of how the Earth revolves around the sun, right? There's 3 different laws that describe how the Earth revolves around the sun. But why does the Earth revolve around the sun? Why does it revolve in an elliptical orbit? Why is T squared proportional to R cubed? Why are the areas equal when the times are equal? Why? It comes down to gravity. We all have this concept of gravity, this general concept of gravity, right? Okay, in fact, my 11-year-old son, I remember when he was like 2 years old, he was playing with Lego or something and it fell over. And he got mad and he says, "Dad, why does it always have to fall over on me?" And I said, well, and without giving him this big detailed explanation of gravity, I said, well, Andrew, I said, every time you drop something, like take a ball and drop it, it falls. Gravity. I said, gravity pulls it down. Gravity pulls everything down. So then my 2-year-old son, next week, drops something, and he gets mad, stomps his feet, and says, "I hate gravity. I hate gravity." Even a 2-year-old can have a concept of gravity, that gravity pulls things down. He has no idea why gravity pulls things down, just that it does. Okay, we now know that gravity acts between any two objects with mass. When we did that silly little demonstration a few minutes ago, there was a force of gravity between you and your partner. There's also a force of gravity between you and your car. It would be a bigger force of gravity because your car weighs more. There's also a force of gravity between you and the Earth, which would be even bigger because the Earth weighs more. There would also be a force of gravity between the Earth and the Sun, which would be even bigger because the Sun weighs more than you do. The bigger the masses we have, the stronger the force of gravity we have. Gravity was first suggested by Isaac Newton. His name appears again. He suggested, as the story goes, we don't even know if this is a true story or not. It probably isn't, actually. Scientists generally think that this isn't a true story. As the story goes, he's sitting underneath an apple tree. An apple falls down and hits him in the head. And all of a sudden, he has this epiphany. The apple fell because it has mass, and it's attracted to the Earth's mass. Therefore, every two objects with mass will attract each other, including the Sun and the Earth. That's why the Earth revolves around the Sun, is because it's pulled towards it by gravity. Just the same as you're pulled towards the Earth, just the same as the apple is pulled toward the Earth, and just the same as, albeit with a very, very, very minute force, you're pulled towards the person that's sitting next to you. We call that Newton's law of universal gravitation. Universal gravitation. Circle that word universal because I want you to understand what that means. Every two objects with mass will pull on each other. It's universal. It doesn't matter whether we're talking about things like the Earth and the Sun that have gigantic amounts of mass, or we're talking about two objects like you and the person sitting next to you that have minute amounts of mass. There is a force of gravity. It is a universal force that acts between every two objects with mass.